good morning, or good afternoon. So, my name is Androwski Spicer. I'm a solution architect with AWS, and I've been here for nearly 4 years. Time really flies. Today, what I will be doing is to present principles and concepts that you can use to be successful within the AWS cloud when defining what your network looks like. Now, can I see a show of hands who are actually, of those of you who were here last year? Welcome back, welcome back. If you were here last year, you'd have seen that the theme I had was simplicity. And it was simplicity in how you thought about interconnecting hundreds or thousands of VPCs and then moving all that traffic back on premises through the AWS network. This year, when I thought about the theme for my presentation, one thing kept on coming back to me, and that is connectivity. Throughout this year, interacting with my customers, I realized that we had to change how we thought about connectivity within the AWS environment. And what this means is we had to get away from only looking at traditional principles like VPC peering and IPsec to really thinking about what do my applications need? Why do I need to connect two VPCs? How am I going to actually route traffic from my VPCs spread out across the world in each AWS region back to on-premises? What does that look like? How do I simplify that? So this year, what I hope to do, or what I will do, is to present principles that you can actually leave here today and implement. Everything that I present here have been done. Some of the Lambda functions and some of the concepts around interface endpoints and gateway endpoints that I will present have been implemented in production in many customers' environments. Now, that being said, this is a 300-level discussion or talk, so I will not spend a lot of time defining things like elastic network interface or what a route table is. What I will do is to spend time showing you or discussing ways that you can actually use it. Now, most of us start with one VPC, and when defining that one VPC and using it, the world seems like a simpler place. But quickly, when we're successful, our networks looks like this, where we have 10 AWS regions, and within each region, we have hundreds of VPCs all spread out across multiple accounts. And the questions we keep asking ourselves is there an easy way to actually interconnect these VPCs that need to talk and to actually move that traffic back on premises? And is there a way for me to actually templatize this type of deployment when somebody new decides to adopt AWS within my organization? I will answer those questions today. But before I dive into it, I want to start with the fundamentals. I want to start by looking at a single VPC and what the recommended approach should be. Because we all start here. The very first thing you do within your VPC is to define the CIDR range that's going to be associated with it. Now, what I recommend is before you actually go inside the AWS console, I recommend that you work with your network engineers. Ask them, what IP space can I actually use for this particular VPC? Because at the end of the day, a VPC doesn't stand alone. You're either going to decide to route traffic internally only within the VPC, or in most cases, customers need to route traffic back on premises. And if you're going to route traffic back on premises, you can't have an overlapping IP address space, because if we identify that that exists, we will drop your traffic at the edge. So work with your network teams, have them provide you with the IP space to be used inside the AWS VPC. The second thing that most customers generally think about, well, what should the size of my VPC actually be? Today, I probably only need 100 IPs. I don't know how large my network is going to get in the future, how many servers am I going to migrate to AWS or build inside the environment. I'm not sure what my adoption rate is going to be. So where should I start? Well, I recommend starting with the largest CIDR block possible within the AWS environment, and that is a /16 CIDR block. Now, once you've defined this primary CIDR block for your VPC, you can't change it. So it's important that you start as large as you can so that it prevents rework or premature rework. Now, the smallest CIDR block you can define is a /16, and as you can see here, this is specific to the IPv4 space. Your IPv4 IP space is fundamental and cannot be disassociated from your VPC. What you can do is to associate an IPv6 IP space with your VPC. And both IP spaces exist under the same VPC ID and operates independently. Even the amount of IP addresses you can actually have is different. So if you look at IPv4 IP space, you have a /16. But with your IPv6 space, we provide you with a /56 by default. And that can provide, well, that provides you with 18 sextillion IP addresses. So the size of your network already is different and much larger. Now, if you're looking to actually use IPv6 within AWS, there are certain EC2 instances that out of the box already comes and with the ability to identify the availability of IPv6 IP subnets within your environment. And when they're created, an IPv6 IP address is attached to these machines, and they can use it without any configuration from you. So if you use Amazon Linux, for example, you have this functionality. Now, one thing to note here before I move on is that these are globally accessible IP addresses. They're global unicast addresses, which means out of the box, you can actually access infrastructure within your VPCs by resources online. So a user online, if they know your IP address, can hit your machines without attaching elastic IP addresses or public IP addresses because they're already public. Now, what happens if the primary CIDR block that you defined for your VPC was a /28, right? You decided, I'm going to test out this AWS thing. You know, I've heard so much about it. Everybody seems to be going there. I don't know what it's about. I'm going to spin up a few machines, and I'm going to see what happens. In doing that, what most customers realize is the ease and the efficiency of the AWS environment to actually do this. And quickly, the decision is made that AWS is where we're going. Now, the problem is the IP space you've defined isn't large enough to support your organization. Now, for workloads that you already have running, do you stop that, migrate them, and create a bigger VPC to support them? Or can you simply modify the VPC that you've already created? Last year, we provided customers with the ability to associate multiple additional CIDR blocks to a single VPC ID. Then we basically added local routes to each route table that exists within your VPC environment so that your network becomes a massive, flat network. And if you look at your route tables after associating additional CIDR blocks, this is what it looks like. Now, there are caveats. If you define a 10/8, if you have a 10/8 network, for example, then you won't necessarily be able to associate a CIDR block, right? So if you already have a network that's 10.1.0/28 or /16, for example, you can't pair to another VPC that has the same CIDR block, nor can you attach another 10.1/16 CIDR block because you already have it. And if you look closely, you're seeing a pattern here. AWS VPC follows fundamental networking principles that exist. So when it comes to having overlapping IP address spaces and working with networks that have those IP address spaces, it can't happen without not being integrated within your environment. Now, to prevent that complexity, I recommend really thinking about your network space within on-premises and within AWS. Another thing that can't happen as well is that if you have a 10.1/16 as your primary CIDR block, then you can't associate a 172.16/12, nor a 192.168/16 IP space with your VPC. Another thing before I move on to subnetting is if you have a route table that has a route in it, for example, it's a 10.1.2/24, you can't define or create another CIDR block with a 10.1/24 IP space. The CIDR block you define has to be smaller than the largest route that exists within your route table. So think about the CIDR blocks that you're going to attach to your VPC and what exists within your current environment. And most of it all comes back to having an overlapping IP address space. Now, the second thing that we do after creating a VPC or defining our CIDR block is decide, how am I going to subdivide that network that I've now defined? What does that subdivision look like? Now, before I tell you what it looks like, within AWS, when you define a primary CIDR block, we take away from you the first 4 IP addresses and the last one. Now, the last one is the broadcast address, and we take that away by default because we don't allow broadcasting within the AWS VPC itself. For DNS, your DNS IP address that AWS provides to you within your VPC is generally base +2 of your primary CIDR block definition. So if you ever want to know what your AWS DNS is, it's generally a .2 to your primary CIDR block. So how should I think about subnetting? Well, what I will say is this. Before actually creating subnets, I would think about what my applications need. Within AWS, a subnet doesn't operate as a VLAN does within your own environment today. That is, a subnet isn't the isolation barrier around a specific type of workload. Instead, a subnet is considered to be a container for routing policies, which simply means that the subnet should actually be defined by the infrastructure that lives inside of it that gives you access to the outside world, whether that is the internet or that is actually routing back on premises. Now, if I should think differently about my subnet, then what provides that isolation for me? Within AWS, security groups, or what we call stateful firewalls, provides that isolation. That's what provides a barrier around that workload that you've now defined. So, should my subnet look like this? The answer is no. Because this specific diagram represents a single VPC. Many of you who sit here today have hundreds of VPC. Can you imagine a world in which you're managing this times 100 or 10 or 1,000? I mean, it becomes a management nightmare for you or your network team. What we do recommend instead is actually putting your subnets in categories. Today, we have 3 categories of subnets. And these 3 categories of subnets can be created and be distributed across all the availability zones that exist within AWS. Now, you might be wondering, why would I do that? Well, a specific reason for it is, within AWS, we always advocate high availability and fault tolerance. A VPC is agnostic to the availability zones that exist, which means it lives in all the availability zones, but a subnet is specific to an availability zone. All right? So if you have 3 subnets spread across 3 different availability zones, it means that you can now attach your workloads to a subnet that lives in 3 different sets of data centers. So if one availability zone goes down, you have peace of mind that the other availability zones are up and running, and users can actually interact with your application. So within AWS, there are generally 3 categories. You have the public subnet, and again, the public subnet is public because within the route table that supports these subnets, there is the internet gateway. Why is that important? Well, in order for you to communicate with the internet gateway, you have to have a public IP address or an elastic IP address. Now, you might be saying to yourself, I associate a public IP address or elastic IP address with my EC2 instance. And you'll be right in that assumption. The thing is, the internet gateway is what keeps track of that public IP address and the mapping to the private IP address that resides on the ETH0 interface of your EC2 instances. The EC2 instance itself has no idea about this public IP address. The internet gateway does, which means that infrastructure with public IP addresses or elastic IP addresses get their access to the internet through an internet gateway. Within the route table of each of these subnets that are listed here is the internet gateway that supports the default route to the internet. The second category of subnets that we have within AWS is the private subnet. And the private subnet, generally, in some customers' environments, the private subnet has no internet access, really. Everything is basically kept within the AWS environment. The route tables defined for the private subnet only has a local route or access back on premises, for example. The third category that we have here is the VPN-only subnets. Now, before I talk about the VPN-only subnets, let's talk a little bit more about the private subnet. For some customers, you have the need to basically update your machines, for example, which means you have to actually reach out to repositories that either exist within AWS, exist online, or some other area. Now, in order to do that, infrastructure that resides within the private subnet must have a means to access the internet. These resources fundamentally do not have an elastic IP address attached to it. So how do you get that access? Well, there are 2 ways. The first, you can choose to associate a NAT instance with the route table that supports your private subnets, or you can add a NAT gateway. And as we go on in this presentation, you will see architectures that actually has both, and I'll speak to when does it make sense to use either, and how are they different. For your VPN-only subnet, you don't have any internet infrastructure in the route tables that support these subnets. What you have is an infrastructure that gives you access back to on-premises through IPsec tunnels. And this infrastructure is referred to as our virtual gateway. And I'll talk a lot more about that as we go on. Now, what about IPv6? If IPv6 IP addresses are publicly accessible by default, how then do I actually make it private? Well, there's several ways. One of which is the routes that you define within the route tables that has routes for IPv6. Another way would be your security groups or your network access control lists. And we'll talk about a third way, which is our egress-only internet gateway that blocks all initiated communication from online with resources that have an IPv6 IP address and allow these resources to be the one initiating communication. So let's take a closer look at egress and ingress designs. When you create these subnets, what is actually added to your route tables is a local route, which simply means that every single subnet that you've created can communicate with each other. It's a completely flat network. So how do you create isolation around these subnets if you have workloads in which, you know what, I have multiple private subnets, but this specific set of private subnets shouldn't have access to any other subnets within my VPC? How do you do that? You do that simply by creating a network access control list specifically for that set of subnets. And you define access policies inside your network access control list, or NACLs, just for that subnet. That's how you actually get isolation at the subnet level. So network access control list within AWS operates at your subnet level. Security groups are attached to the network interface of your EC2 instances. As we spoke about, infrastructure within the public subnet has access to the internet gateway. This is very important, because if I implement, for example, a Palo Alto device to do layer 7 packet inspection, but I have resources with public IP addresses, how then do I ensure that these resources are actually, that request to the internet is routed through my Palo Alto infrastructure, right? It's very important to actually know that these resources with public IP addresses from AWS will access the internet through the internet gateway and not that infrastructure. Now, as you can see here, if you look at this route table, you'll see that there's a local route for your IPv6 space, and there's also a default route for the IPv6 space. It's very important to note that we handle both IPv spaces differently, and both IPv spaces have limits that are independent of each other. So if you look at something like the limitation on a route table of 100 routes, that's specific for an IPv4 IP space. Now, if you also look closely, you'll see that access to the internet here goes through two different infrastructures. IPv4 goes through a standard internet gateway, and it's important to know that an internet gateway can handle both IPv6 and IPv4 routes. So if you had no need to block communication from initiation of access from online to your IPv6 space, then you could do away with the egress-only internet gateway here and simply have everything go through your internet gateway. So let's talk a little bit about your VPN-only subnets and how they gain access to your on-premises environment. In order for you to actually establish IPsec tunnels to on-premises, you have to define the attributes of the firewall or router that exists within your on-premises data center. Within AWS, that definition is considered to be a customer gateway. For a customer gateway, you define the public IP address of that device. You tell us what the BGP ASN is, whether it's public or private. If you own the ASN, then you can specify it. But if you don't, you can specify a private ASN. Now, once you have that established, you can then create multiple IPsec tunnels between your AWS environment and your on-premise router or firewall or layer 4 multi-layer device. Now, when you do that, we create two tunnels. If you leverage static routes, for example, you have to specify within the AWS environment that these are CIDR blocks that I need to advertise into AWS. If you leverage a more dynamic routing protocol, which today we support only BGP, then you don't have to specify the CIDR blocks, because once you advertise those routes via BGP, they'll be propagated to your route tables that your virtual gateways are attached to. So, private subnets. How do they gain access? As I said before, you have the ability to attach a NAT instance to the route table that supports your private subnets. The good thing about actually having this is that you can actually SSH to this instance, and you can add configuration to it. For example, you can add layer 7 packet inspection using infrastructure like Squid, for example. The thing is, you have to actually manage the availability of that NAT instance, right? Not only that, you have to manage the access, which means that the network interface card for this particular instance has to support the number of requests coming in to go to the internet. Now, as your environments scale and as your environments grow, you don't necessarily most customers don't necessarily want to manage the NAT instance. They want something that's more scalable. What we provide today is the NAT gateway. And a NAT gateway is highly available. It scales based on what you need. And the good news is you don't manage this. It's AZ specific, which means that you can create a NAT gateway in each and every availability zone that exists within the AWS environment, and then zone your internet traffic through a NAT gateway that's specific to that particular availability zone. And if you're wondering, that's what we recommend. Now, I want to touch on one thing. And I'm always happy during my practice when I came up on this slide, because ever since I started working at AWS, and ever since I started talking about VPCs, customers have asked me, yeah, you guys have public IP addresses, but I also have public IP addresses. Can I carry my public IP addresses to AWS and use those with my NAT gateways and EC2 instances and load balancers? And the answer then was no. Today, you can bring your public IP address space if it's registered to a company and if it's registered with RIR, or the Internet Registry, which means that when creating things like NAT Gateway, you can specify your own public IP address, and AWS will advertise that IP address space to the internet for you. So that's all good and dandy. We have routes to the internet. We have routes to on-premises. But that's not the only thing I route to. Most of my requests that I have today goes to AWS services, like Kinesis and API Gateway. How do I gain access to those services privately? Do I have to go through your internet gateway? I don't necessarily want internet access in my VPCs, so how do I stem that? Well, today, we provide two types of endpoints. And endpoints were created to give you private access to AWS public resources, which means to access something like Kinesis, to access API Gateway, you no longer have to go through the internet. You can go through optimized network path, specifically designed for this kind of interaction. Now, we have two types, gateway endpoints and interface endpoints. Gateway endpoints was the very first generation of endpoints that we created. And these provide access to two specific services. The first was Amazon S3, and the second is DynamoDB. Now, if you look close at this slide, you'll see that my internal apps are communicating through a specific route table to these AWS services, which means that when you create a gateway endpoint, you specify the route tables that should have access to this endpoint. Once you do that, we add a specific route to these services. So every request you make to S3 now goes through the endpoint by default. You don't have to manage that leg of it, nor do you have to manage the availability of the endpoint infrastructure that supports your VPC. Another thing that we do for you is give you the ability to define endpoint policies. And an endpoint policy basically tells us what resources have access to this endpoint and what resources can this endpoint actually access. So if you look at S3, for example, I can specify the principals that have access to this endpoint, and then I can specify what buckets this endpoint can communicate with. To add another layer of security within my bucket policy, I can specify that the principal that actually has access to this particular bucket is this specific VPC endpoint. So even outside of the networking layer, if you look at just fundamental security within AWS, you have added security for access to different resources. And the same, except for bucket policy, is true for DynamoDB. Now, okay, great. So I can access DynamoDB and S3. But I don't necessarily, that's not the only services that I use. I'm using Kinesis a lot these days. How do I actually gain private access to that? And what is the difference, really, between an interface endpoint and a gateway endpoint? Well, an interface endpoint gives you the ability to create network interfaces inside subnets in your VPC to act as an entry point for services like Kinesis that exists within the public space for AWS. Because this is a network interface, you can then do things like add security groups to your interface endpoints. Now, it's important to note that interface endpoints allow you to communicate with services that are powered by private links. And the network interface is managed by AWS. Now, not all services that AWS provide actually exist within all the availability zones. So it's very important that when you decide to use an interface endpoint, that you do a describe VPC endpoints to see where these services actually reside, so that you can create network interfaces in the AZs that they're available. So after doing describe VPC endpoints, you then go ahead and create your interface endpoints. You don't specify, in most cases, an endpoint policy for the interface endpoints. What you specify is a security group that determines which subnets within your VPC actually has access to this network interface. Now, one of the big differences between an interface endpoint and a gateway endpoint is that interface endpoints can exist for services outside of just AWS public services. And I'll talk a lot more about this when we talk about VPC endpoint services. Now, once you create your VPC interface endpoint, we generate DNS hostnames for you, generally in 3 categories. The first is just an endpoint hostname that you can use to actually communicate with a particular service. The second are specific availability zone hostnames, so that you can basically build inside your environment or your application zones. So you can decide which hostname to use based on the availability zones that your applications live in. You access VPC interface endpoints through these hostnames. So unlike gateway endpoints where we have a route added to your route table, with interface endpoints, you access these services through the DNS hostnames that we provide for you. Now, it's very important to note that if you're interacting with an AWS public service, like Kinesis, for example, then we recommend that you enable private DNS, private DNS. And the reason for this is, once you enable private DNS, AWS will associate a private hosted zone with your VPC for this AWS service, and will add a record set to your hosted zone that resolves to the private IP address of the network interface that exists within your environment. Which means that if you're communicating with Kinesis today, you'll see no difference. All right, so if you have an application that's writing to a Kinesis shard, for example, you won't have to make any special changes to your application. All requests will go through the fundamental DNS hostname for Kinesis. How do I use this? Great, it exists. But what are some of the use cases? I've seen customers create solutions to problems that would generally require a VPC paired connection. One such solution here that we have, a specific customer of mine actually had a set of application servers, and they wanted to write to a Kinesis stream. And once written to a Kinesis stream, they wanted to get that data to the Elasticsearch cluster. And that Elasticsearch cluster was not publicly accessible. It was only accessible within their VPC. So the problem was, well, I don't want to use Kinesis firehose. I really want to use Kinesis streams, so how do I do it? So what I created as a POC for that customer was this solution. On the left, you can see a Lambda function that writes directly to an Elasticsearch cluster. This Lambda function is configured to work only inside the VPC, and is triggered whenever something is written to a Kinesis stream. Now, the applications themselves need to get data to that Kinesis stream, so how does it do it? Well, I created an interface endpoint for Kinesis and allow the application to write to Kinesis as it would if it was writing to Kinesis as a public service. The only difference is data being written to Kinesis is automatically routed through the interface endpoint to the Kinesis service. There's no access to the internet. All of this happens in a subnet that doesn't have any access to the outside world. OK, great. So if I write data to Kinesis, how do I get my Lambda function to actually take that data and write to my Elasticsearch cluster? Well, in this scenario, the Kinesis service, even though public, will make the call to the Lambda service itself, and the Lambda service create your Lambda functions inside the VPC, which means that it has a private IP address from a subnet that you defined, and it can communicate with the Elasticsearch cluster that exists. So that Lambda functions takes that event data and writes that Kinesis stream time series data to your Elasticsearch cluster and gives you the ability to visualize that data using Kibana. Now, great. That's done. But how do I persist this data? The solution for that is having that Lambda function also do a call to S3. And if you look closely here, that is actually happening through a gateway endpoint. So you can have both operating simultaneously within your environment. Now, one thing I'd like to touch on as well is there are creative ways to gain access privately to your environment. One such way that I see many customers are using today is our API gateway. You have the ability to create private APIs. You also have the ability to create a VPC link between infrastructure that sits behind a network load balancer and API gateway. And this is one such scenario. And this is also a scenario that customers of mine have implemented. OK, so I spoke about VPC endpoints, interface endpoints having the ability to interact with AWS public services. But you also have the ability to create interface endpoints to solutions that exist within our marketplace, but also to solutions that you create. So if you created an environment and you want to share that environment with multiple accounts, do you then have to create multiple peering connections or IPsec tunnels? The answer is no. If you meet the requirements for creating endpoints or endpoint services within AWS, then you can basically whitelist those accounts and have them interact with this specific application through an interface endpoint. And access to this environment is only initiated by by the accounts that you've whitelisted. The person who owns this environment can't reach out into the other environment and interact with that customer's resources. So intrinsically, there's a layer of protection there for you. OK, so let's talk a little bit more about what it actually looks like. So the very first requirement for creating endpoint services is that your application must be an application that supports TCP only and sits behind a network load balancer. Once you have that set up, then you go ahead and create a VPC endpoint service and associate the network load balancer that you've specified for this specific application with this endpoint service. Then you whitelist the accounts that must have access to this environment. Now, as a consumer, in order for me to actually create an interface endpoint, first, my account must be whitelisted, and second, the producer must accept my request to interact with that set of applications. So as a producer, once you've whitelisted this account, you then authorize it when an interface endpoint is created to this particular application. OK, great. So what can I do? Well, a very simple example of how customers are using this today is this. And in this particular example, what the customer has actually done is to front-end their SQL server with a network load balancer. And instead of creating peered links or IPsec tunnels to share this database with another set of accounts, they've simply created an endpoint service from this implementation and then whitelist the accounts that have access to it. So if you look closely here, this SQL server is configured with a notification when a failure event actually happens. And that failure event is written to a SNS topic, and subscribed to that topic is a Lambda function that is triggered when something is written to this particular topic. That Lambda function then checks the network load balancer to see what IP address it has. And if it has the old IP address, it removes the old IP address and replaces it with a new IP address if a failure occurs and you switch over to your standby SQL server for RDS. And all of this is happening within your VPC. There's no access at all to the internet. OK, so everything we've spoken about so far really revolves around a single VPC and that kind of access. But many of you have hundreds and thousands of VPCs. We haven't spoken about really how I create connections between those VPCs and simplify routing back to on-premises. So how do I do that? Why not one big VPC? What are some of the reasons for having multiple VPCs? And I'm sure some of you asked yourself that same question when you initially started using AWS. But what you quickly realize is that the different use cases and the different compliance requirements that you may have drives you to have multiple VPCs. So you end up with environments like this, where you have prod VPC separate and apart from dev VPC, because nobody wants API limits that exist within AWS to be exhausted by dev and then bring down your production environment. So you create multiple VPCs to overcome these limitations. You also don't want your DR facility or your DR environment to be in the same VPC or account as your production environment. So these decisions drive isolation at the account level and at the VPC level. So now I have all these VPCs. What does AWS actually recommend? Well, first, customers generally go the route of creating IPsec tunnels to every single VPC. But quickly, you realize that for each VPN that you establish to a VPC, you get 2 tunnels. So if you have 14 VPCs, you're having 2 tunnels being created each to these VPCs. So you end up with 28 tunnels to manage. And if you have 200 VPCs, now you have 400 tunnels to manage. So the second thing most customers generally do is to create what we call a shared services model. And that's where they've replicated the infrastructure that exists on premises, like Active Directory, for example, DNS, into the AWS environment, into a single VPC, and then create peered connections between the VPCs that need access and the single VPC. The problem with this design that you'll quickly realize is that there's a limit on the number of peered connections that you can create. Not only that, the first thing you realize is once you peer 2 VPCs, you've basically joined 2 networks, and they become one, which means that you can basically route traffic to all subnets that exist within each VPC, which creates the scenario of, OK, so now I have one massive network. How do I protect my workloads? Because I simply only wanted to give one subnet access to that VPC. And the answer is security groups. The second thing you realize is there's no transitive routing. So even though I have all these VPCs connected to the shared VPC, I can't send traffic through the shared VPC to another VPC. So I can't interconnect VPCs seamlessly. Now, before I move on to other scenarios, it's actually important to note here that if you have a shared services model, where you have something like an IPsec tunnel between a shared services VPC and on-premises, and other VPCs connected to it, you can replicate that design globally, which means in another AWS region, you can have a shared services VPC that supports that specific region, for example, and then replicate data between shared services VPC using inter-region VPC links. And by using inter-region VPC links, you're now basically leveraging AWS's backbone to move your traffic, reducing edge routing, and gaining some of the functionality that you're looking for. Now, great. I have an IPsec tunnel between my shared services VPC and my on-premises network. But I get 1.2 gigabit per second of bandwidth per tunnel. That's not what I want. I mean, that doesn't meet my requirements. I need gigs and gigs of bandwidth. How do I achieve that? How do I get more deterministic latency between the AWS environment and my VPC? And how then do I access AWS public services from on-premises? And the answer is direct connect. So we created direct connect to give customers a more deterministic latency between their environment and AWS. Not only that, we created direct connect to remove the need to have internet to actually communicate with AWS VPCs across the internet, or AWS public services across the internet. So with direct connect, you can create private and public VIFs. Private virtual interfaces communicate with the virtual gateway, for example, of your VPCs. And public virtual interfaces communicates directly to AWS sets of public services. Now, both supports IPv6, and you must have unused VLANs within your environment, and your infrastructure must support 802.1q in order for you to actually establish connectivity, BGP relationships between AWS and your on-premises environment. One of the new additions that we've done recently is to provide the ability for you to leverage the LACP protocol to create lag groups, which means that if I have two 10-gig links within the same direct connect facility, I can represent that as a single interface of 20 gigabit per second by leveraging LACP. Now, great. So I have direct connect, but I also have VPCs all over the world, right? Do I then create direct connect links and connect that to my MPLS network, and then backhaul that traffic through my MPLS network that needs to get to each region? The answer is no. This was the design once upon a time. Last year, we made a step to remove the need for you to backhaul that traffic across your network and to simplify how you associate your VPCs with on-premises. And that association came through the Direct Connect Gateway. The Direct Connect Gateway was built to remove the need for you to create a private virtual interface to each and every single VPC that you wanted to connect to. Instead, if you have 100 VPC that exist within, for example, the Oregon region, you can simply create a Direct Connect Gateway and associate all those VPCs with your Direct Connect Gateway, and then establish your BGP neighbor relationship between your on-premises network and the Direct Connect Gateway itself. The Direct Connect Gateway will then propagate the routes it learns from your VPCs to your on-premises network. and vice versa. So instead of connecting your direct connect links that are global to your MPLS network, you then create virtual private interfaces to the direct connect gateway, because the direct connect gateway is a global infrastructure. Now, what else can I do? Can I access interface endpoints across regions? So if I have a service that I've created and I've advertised that as an endpoint service, right, and I've created interface endpoints to it, can I then access that through an inter-region VPC peering? The answer is yes. But this still provides challenges. Come back to this. This still provides challenges. And the challenge it provides is I still don't have my VPCs peer interconnected. No, I have connection back on premises. But how do I actually route traffic between my VPCs and get that functionality? Because the Direct Connect Gateway doesn't provide that. You can't do transitive routing through Direct Connect Gateway. So what do I have that does that for me? And the very first attempt at actually achieving this seamless connectivity was to introduce the Transit VPC. And the Transit VPC used a software appliance like a Cisco CSR 1000V router, which gives it the ability to create IPsec tunnels to VPCs across the world, but also create an IPsec tunnel or a connection to a direct connect link back to on-premises. The thing with that is you had to manage those tunnels and the infrastructure that supported it. So what did AWS do with your feedback? For simplicity, we created the Transit Gateway. And the Transit Gateway acts as a layer 3 hub for your VPCs that exist within AWS. What does that mean? The very first thing I'd like to say to you is that it simplifies how your VPCs all communicate and how you define edge routing within your AWS environment, which means that the Transit Gateway will be the central point through which all your VPCs talk in order to get to another VPC. So out of the box, you have transitive routing happening. Not only that, but you can actually define environments or Transit Gateway definitions that actually allows you to communicate amongst VPCs and also on premises. So the Transit Gateway becomes that single point of communication for you. No longer do you need VPC paired connections in order to talk amongst VPCs. That limitation is gone. So what is it? It's important to know that a Transit Gateway is a regional service, which means you define a Transit Gateway per region, and you have the ability to attach VPCs that exist within that region to this Transit Gateway. This Transit Gateway has its own route tables, and the route tables themselves do not have the limitation that your VPC route tables have. You can support thousands of routes. Today, the Transit Gateway supports IPsec tunnels. So you can create a single set of tunnels, or you can create up to 50 or more tunnels, for example, within AWS, and add the routes for the networks that those tunnels connect to your route tables for Transit Gateway. So what are some of the use cases? Well, the very first use case is, well, I have all these VPCs. I really want them to talk, but I also want them to have the ability to route to back on premises and give my users on premises to interact with resources that exist within these VPCs. So the first use case is really using this Transit Gateway as a central hub, layer 3 hub. So you build a hub and spoke network within a Transit Gateway. So basically, you've defined a single route table, and within that route table, you've basically associated all your VPCs and the IPsec tunnels that gives you access to resources outside of your AWS environment. Now, I know most of you might be thinking, so do I have a virtual gateway connected to my Transit Gateway? The answer is no. The Transit Gateway has the ability for you to define and create these IPsec tunnels. And by saying that, it's important for you to note that a transit gateway isn't built inside a single VPC. When you create a transit gateway, the first thing we do is we ask you to specify the subnets within the VPC that you want us to create the network interfaces that gives your transit gateway access to your overall VPC subnets. And I'll repeat that. When you create a transit gateway, we create a network interface in a single subnet per availability zone that gives us access to all the subnets within your VPC. We recommend that you specify more than one availability zones in order for us to have high availability. So if a network interface that we created in a single subnet within a single availability zone goes down, we have another option to get to your VPC. If that's the case, what architectures can I then create? Now we'll talk a lot more about that in a few slides. Now, the transit gateway, even though you create it within a single account, within a particular region, you have the ability to share this transit gateway to multiple accounts, whether you own those accounts or they're external to your AWS organizations. Now, if I can share my transit gateway with resources inside my AWS organizations, then can I just simply specify an OU within my organizations to share this transit gateway with, and then have all the accounts that fall within that OU having access to my transit gateway? The answer is yes, which simplifies how you share your transit gateway to accounts, to multiple accounts. Now, how you do this particular share today is through the Amazon Resource Access Manager. That's a new service, and that service allows you to basically share seamlessly infrastructure or services within your AWS environment with other accounts. Once you've actually shared your transit gateway, accounts that you've shared it with can discover the transit gateway and basically associate their VPCs with the transit gateway, which means that once that association is finished, they can then add routes to their route table to get to other VPCs through the transit gateway. And I'll show you what that looks like in a second. Again, for every association that you make to a VPC, a successful association, a network interface is created within the subnet that you define for that association. OK, so what does routing look like? Earlier, I spoke about one particular use case where I've used my transit gateway as the central layer 3 hub. But can I gain VRF-like or virtual routing and forwarding functionality within AWS through the transit gateway? And the answer is yes. You can define or you can create multiple route tables and multiple route table associations that allow you to segment VPCs and what those VPCs have access to. So if you have dev VPCs and you have production VPCs, these VPCs can all live in completely separate route tables, having access to different infrastructure or different ways of accessing your network. Another scenario that you may want is, well, I have all these VPCs. I don't necessarily want them to talk to each other, but I want them all to be able to communicate with my on-premises network. You can create that routing configuration within AWS. Now, within Transit Gateway, within the routing sphere, you can create, well, by default, when you create a Transit Gateway, you specify a BGP ASN number, and you specify not only the description and the name, but should there be a default route table, and should I have propagation to this default route table automatically. Now, once you've defined that, whatever association you have, whatever VPC is associated with your transit gateway, they propagate their routes to the route table that they're associated with, which by default is a default route table. What does that mean? What routes do they actually send? The routes that each VPC send is a local route that exists within their environment, their VPC route tables. So let's look at some routing scenarios. Now, one of the routing scenarios, we're going to look at 4, actually. One of the routing scenarios I'm excited to show you is how do I centralize access to the internet using Transit Gateway. So each VPC don't have their own access to the internet anymore. I have a single VPC that acts as my egress point for all the VPCs that I have. Now, to make this possible is the elastic scaling that Transit Gateway does on bandwidth. It scales this bandwidth to achieve the data throughput that you're looking for. So each association that you make has the ability to actually send 50 gigabits per second of traffic. So let's look at this particular scenario. In this scenario, we're basically associating 3 VPCs with the Transit Gateway, and we're specifying how each VPC reaches the other. So if you look at account A on the top left-hand corner, it has a local route specified, but it also has a route specified for accessing the 10.2 network by going through the Transit Gateway, and the 10.3 network by going through the Transit Gateway. And if you look closely, you'll see a 172.16/16 route being specified that goes through the Transit Gateway as well. That 172.16 is the route for accessing resources on premises. And if you look at the Transit Gateway's route table, you'll see that there's an IPsec configuration there to the 172 network. So within the Transit Gateway's route table, what you'll see is a destination and the next hop infrastructure. Now, one thing I would like to do before I end here is to actually have you take a close look at the VPN connection between the Transit Gateway and your on-premises network. One of the fundamental differences here is that you can have multiple tunnels and load share across those tunnels using ECMP, which is equal cost multipath. So by doing this, I can then have 5 tunnels, 5 IPsec connections, and I'm load sharing my request on premises across these connections that exist, if the advertisements that are coming are the same into AWS Transit Gateway from these IPsec tunnels. Now, these slides will be available after the conference, so you can take a look at all the different configurations that I have here. That's it for me today. Thank you very much for your time.